start the lecture. Okay, there is no title written here, but the title that I should say that we continue to talk about quantum affine SL2. So let me recall the slide with the definition of this algebra. So this algebra has a Drinfeld-Jim representation, generators E0, E1, K0, K1, F0, F1, which is 5 standard relations here, written here, and a coproduct, standard coproduct. What we succeed in the last 2 lectures. First of all, we succeed 2 goals. First, we defined so-called root basis. So to any root, not necessarily simple, we defined certain element which belongs to nilpotent subalgebra, n plus or n minus. Okay, let me copy my favorite picture from the previous lecture. This one. And put it here. Okay. Sorry, no space, but I move it. Okay. So for any root element here, here, and so on, we defined for any root, we define the root element in the universal development of the nilpotent subalgebra. And let me recall that for these elements, for these 2 columns, they're defined via the braid group action. And these ones are defined via coproduct. No, via as Q commutators. The box here. They're defined as Q commutators. Then we defined negative elements which belong to UQ and plus and minus. And in this way, we get PBW basis for the full affine quantum group. This was our first goal. So what? Okay, let me make the slides with such with this story. What we know. So what we know the vectors E beta for any beta simple for any beta, for example, positive root. We know F beta, F minus beta again for any beta in positive root, and we have P BW0. This is this, from my point of view, more or less result of the lecture 4. And the result of the lecture 4 was, among many corrections to the lecture 4, was the statement that we know another realization of this affine quantum group. This realization is usually called new Drinfeld realization. And actually, we will talk about it. I mean, at least in the final slides, we will talk about it. Maybe we will come to this during the lecture. But let me say that this relation is defined in form of, we have elements of the X plus, X minus, and also Heisenberg algebra. and commutation relations. And these relations look like affinization of the relations of the affine quantum SL2. So for example, commutators of x plus and x minus give us something like Cartan. This exponent of H, this is again exponent of H. H is a Heisenberg. Commutator H and x plus gives us x plus. This is a version of 2 which we had in SL2 relations. And also these also relations. And this relation, of course, I can't explain so easy, but we anyway we deduce it. So this is 2 points which we know, and our goal for today is to study coproduct. Before we talked just about algebra itself. We work with commutation relations, work rather hard, and so on. But quantum groups are very interesting due to the fact that they are Hopf algebra, they have coproduct. So we want to study it. And in particular, we want to have a matrix, and in this case, it will be so. So we want to have universal matrix. And the new feature, which is already not very new, which already appeared in the not affine quantum groups, but here this is much more important, much more transparent. That when I say coproduct, I actually have to say which coproducts. There are, in this case, we have many coproducts, and some of them are quite similar, and some of them are not. Any questions? Okay. We want to study this for affine case, but half of the steps were actually the same as they were for non-affine case. We will use the braid group in order to study. So I recall how to work with non-affine case without proofs. These results were stated or proved. Some of them were stated, some of them were proved in the lecture, in the course last year. First, let me define the following for any root. Beta, let us define the corresponding local contribution to their matrix. This should resemble to you a matrix for ordinary SL2 case. For ordinary SL2, we have just one root, just E, and so we have the same formula, but without this beta. If algebra will not simplify, then this Q will have some indices. But for simplicity, I talk about simplized case, or better to say, case where all real roots have the same matrix. Okay. Theorem. which we will need is the following. So if we conjugate our coproduct using automorphism del Ti, which I recall is automorphism from the braid group, then the coproduct will be just conjugated by this matrix R. Ri is here. Ri is R alpha I. This generators braid group generators Ti are defined for simple root, so this R corresponds to simple root. What does it mean? It means that actually we, according to my remark that we have many coproducts, actually we see this fact that we have many coproducts already here. So for any, in principle, for any W affine value group, we can define a coproduct delta conjugated delta W, which is delta conjugated by TW. For example, we can do this for simple reflections, because TW is an automorphism of the algebra. Then the new coproduct will satisfy all axioms. And theorem says that this coproduct will be conjugated to the initial one. So in this notation, this is something like delta I. Delta. Yes. Oh, maybe. This theorem says that all these coproducts are actually conjugated. This is a part of the proof for the formula for the universal R matrix. The goal of the universal matrix is conjugate two coproducts, delta and delta opposite. And using this braid group, we can conjugate, we already conjugate some coproducts. Somehow in the limit, we will conjugate delta and delta opposite. Okay. This
so the delta opposite will be something like delta times the longest element.
For finite case, yes, something like, and plus some. I mean, if it was like this, then universal matrix will be just the product of these R's. But universal matrix has also contribution from Cartan. Mm-hmm. This plus some automers additional. Other questions? Okay.
Сейчас, а вот если можно вопрос, то есть получается, что если у нас там, не знаю, ну что это же бесконечное число этих коумножений, да? То есть, ну так группа кос бесконечная.
In principle, yes, I could define this not for, I wrote formula for element from the affine while group, but this is not necessary. I can say for any. But as usual, I think that, how to say, you can compute that Ti squared is some automorphism, some simple automorphism like conjugation, I think. Okay, well, no, I'm not sure, 100% sure. So in principle, yes, it's infinitely many couples. Okay. This formula can be used in order to compute coproduct of the root elements. Corollary. We can compute here I use inequalities. What do I mean here? Let me recall that if we fix the composition of the W0, maybe I can copy it from the first lecture. We have some order on root generators, which is actually used in the definition of okay, let me show it here, which is actually used in the definition of the PBW theorem, in the statement of the PBW theorem. So if we have the composition longest element, then we define betas by these formulas, and these betas are all positive roots in some so-called convex order. And here the product goes over gamma which are less than beta in this order. Maybe to make it more clear, let me recall the proof of the theorem, this corollary, because it is easy. Well, the difficult part is theorem. The proof goes as follows. So we have this T beta is a product actually ordered for gamma less than beta, T gamma inverse of E alpha for certain alpha. In this formula, you see any beta is obtained as composition of certain reflections to simple root. And the formula in the definition of the root generators, we also have the same. We take simple root generator and apply T inverse several times. So we do the same here. Maybe I use wrong convention. So here, as the numbers are greater, then let me also write here inequality in the opposite direction. Okay, so this is a definition, and what of E beta, and I have to compute delta for such product gamma operated on beta, T gamma inverse on E alpha. And using the fact that we know how delta commutes with coproduct, we get that we get the formula that this is a product of L greater. R beta inverse R gamma. Delta of E alpha, product of and we know coproduct of E alpha, so we just substitute it here. Sorry, I made it. This was wrong. This is here, and so here T applied to this coproduct. And this leads to the desired form. Okay, no questions.
But one of the products of R's runs in one direction and the other is the other one. Yes.
Yes, yes. The one of these products should be inverse to each other, to the other.
And this is only real roots.
Yes, this is only for real roots, for roots for which we have formula like this. So if root is obtained by the action of the sum of the braid group, then since we know how braid group commutes with the coproduct, we can compute coproduct of the corresponding root. Okay, and let me state corollary of this theorem. Of this corollary of the corollary. It says that for any beta, we have the following formula: delta of E beta is equal to E beta times K beta plus 1 times, here should be E, of course. Plus, first I write somehow misleading, somehow sloppy, low terms. And by low terms, I mean that here we take the product of such R gamma, where R gamma is greater than beta. So the element which we obtained here, the all, how to say, if we take anything from here, how to say it better, so all these R gammas, they do something in the second term. And okay, by low terms, I mean that this belongs to u greater than beta plus tensor u, I think, less than beta minus, maybe like this. So what can we get on the, so this load, I mean, okay, I can try good formula just now. I'm not so good prepared for today, but I'm just trying to explain the idea that due to these terms, we can have some control on the corrections. So this is a coproduct like it was for simple roots, and this term controls corrections, and we can say that this correction, they are somehow triangular because all these factors are triangular. Okay.
Okay.
Okay. From this corollary, we can get some sort of proposition. Let me think, do we want to state it now or maybe later? So, okay, our goal is the following. So we want to prove the PBB bases which we constructed are orthogonal with respect to pairing between n plus and n minus. So if we have pairing of some f gamma 1 power n1 blah, 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 f it will be product of delta n, I don't know, for some number L from 1 to n capital, delta L n NL and something. Experience with SL2 says us that it will be such numerator, such denominator. Given some power. And I claim that using this corollary helps us to prove this. Indeed, this pairing is equal to pairing of f gamma 1 on times, and so we can move away one factor. Move away one factor.
Миша, какому соотношению у нас, каким свойством у нас удовлетворяет вот это вот спаривание?
This pairing is invariant pairing between n plus and n minus.
Ну то, что там.
What we had in the first lecture, this sort of properties.
А запятая BC это там копроизведение в одной стороне. Ну да.
Property like this.
Угу. Спасибо.
Okay, and then so on the right side we have product of coproducts. powers. And if we take something not from f gamma 1, but from something different from here, then the parent will be just 0. This follows from such triangularity. This triangularity says that if we take something from these terms, even L and so on, we cannot get the weight gamma 1. So this f gamma 1 should somehow talk only to this, and from here it should talk only to the first term. This is how this is the logic, and then we can compute and get that this will be something like this number 1, and then we get the pairing where we have 1 gamma 1 less and 1 gamma 1 less here. This number appears as we should take e gamma 1 from the first factor from one of these, but we don't know from which one, and therefore we have M1 possibilities which differ by certain q's. So this part of the logic was actually for non-affine case. I mean, so everything works for for any. I mean, it's not necessary, but for example, in this formula where I wrote that I obtain all my simple roots, all my root generates by action of t inverse in some power. Here I already use it. We are living in finite case, because in a finite case we have two possibilities. Okay, here's the picture. So we have roots of we have three types of roots. Let me maybe use some notation. So let me denote. This is a new point. Phi plus infinity is a set of roots of the form alpha plus and delta for n greater than or equal to 0. Phi minus infinity are positive roots which are obtained from the negative root of the finite root system. And we can, in principle, we can define finite subsets here. And also I defined the same with imaginary roots. So phi plus infinity bar is phi plus infinity plus imaginary root, and the similar for minus. Then the logic from here works for either if we take all roots from the phi plus, or either if we take all roots from phi minus. All roots from phi plus are obtained by the action of t inverse. They are obtained by the action of the translation in negative powers to some root. So for these roots, everything is okay. Similarly, for these roots, everything is okay. But we don't have control about on their relationships, and actually we do not have control on the coproduct and pairing for the imaginary roots. So this is what we have to study now. You see, I'm not so prepared to write down everything for detailed formulas, so I'm just trying to explain idea. Are there any question about idea? How to study pairing? What we want to do, and how, and so on. Okay, no. The result of the previous discussion should be, for example, stated like this: that we have the following lemma. If we take element of from the right column, so take a product of d delta alpha plus n delta, then it will equal to the standard part, like for simple root, plus correction, and in this correction, low terms, and these low terms they belong to the u plus n minus 1 times u minus, something like this. So correction which we have on the first part is a combination of the, so if you take a product of some root, then the correction is a combination of the roots below it. This triangularity property which we I think have. The next task is to study imaginary roots. And this is even for SL2, this requires some computations, which are not very easy. For imaginary roots, we do not have the braid group in order to study them somehow in obvious manner. We have only definition as a Q commutator. Let me give one computation and then state the results, general results. So computation. So we want to compute delta of E small delta. Let me recall that E small delta is a Q commutator. Now we just substitute the definition. Okay. So for E0 and E1 are simple roots. So we know all terms. Okay, maybe have problems with space. Okay. This is equal to. First, we will have term where we have E on the first factor and K on the last factor. So here we take this term, here we take this term, and clearly this will be just E delta times K delta. Then we will have terms where we have both e on the first factor and the second factor. So what first it will be if we take e0 on the first, e1 on the second, then we get e0 times k0 e1. Probably it will be total sign should be minus q inverse e0 times e1 k inverse. Similarly for the e1 on the first factor, e0 on the second. And the last term will be if we take the last factors everywhere, so it will be just 1 times e delta. And now we see that one of these factors, I think this one, actually vanishes. So the sum is equal to standard term plus what we have from the second plus something like q in power -4 - 1 e1 times e0 k1. And I want to say that this is a correction. And this correction actually belongs to phi, to universal enveloping, to the subalgebra generated by the roots from the first column times universal enveloping subalgebra generated by roots from the last column multiplied by u0. Here we have a couple. So the claim is that this is a general fact. Okay. That delta of HR is
Сейчас, а как нужно еще раз понимать вот эту принадлежность? Не очень понял.
So the first factor is the subalgebra belong to subalgebra generated by first column. Let me copy. This element E0 belongs to the first column, and this element belongs to the last column multiplied by some element of the cartan. Okay. In principle, E delta is symmetric, so it could be in the opposite way. So it could be the features that term where we have E0 on the first factor, E1 on the second factor, that such term vanishes. And this I wrote as such embedding conclusion. One, is it okay?
Okay.
The claim is the same statement valid for any R plus corrections. And these corrections belong to the same space. So this should be viewed as an analog of the triangularity which we had here for real roots. So for any root, we have somehow preceding roots in some order, and for root alpha plus and delta, preceding ones are here, and for imaginary root, preceding ones are all here, and only them can appear as the first factor of the couplet. Okay, so maybe I should say that before, but let me recall what is HR. I defined it last time, but maybe everybody forgot that they defined by the formula that 1 plus Q minus Q inverse sum of n greater than 0 n delta is the exponent of the r greater than 0. And I lost the corresponding z here. For example, the first one, H1, is actually E delta up to some Q inverse, which is not important. Actually simplify this formula. For this formula, it is important that we take these H's, which are like Lie algebra generators, contrary to this full current, which is like Lie group type. Okay, so using this triangularity, one can prove that the PBW bases which we constructed are actually dual to each other. And one can compute the exact form of the pairing between dual elements. And finally, this leads to the formula for the universal matrix. And the formula will be the same as we had in finite case. Let me find it. Where now this product is actually infinite. So first it goes over the root like alpha plus and delta, then root like and delta, then root like minus alpha plus and delta.
Против часовой стрелки?
I mean, there are two formulas. Actually, maybe for me, I prefer to say in the opposite order. Maybe, but I don't have formula. I mean, this depends on the conventions. I'm not sure that my conventions agree with the choice which I do here. In one order or another. Which one is correct, I'm not sure. Okay, so this is what I want to say about this factorization formula, like Horoshkin-Tolstoy formula. And I mean, I'm not, you see, I'm not in very good health, so I don't want to go over time, since I don't, and better to explain what is the subject and then and then stop. But so I have in the subject have one more piece of information, which is about new realization. So I already recall that we have new realization, and actually the Drinfeld defined not just new realization, but new coproduct. He defined the coproduct in terms of these new generators, and approximately this coproduct looks like delta of x plus is equal to x plus times psi plus plus 1 times x plus. Delta of x minus is equal to x minus times psi minus plus. Oh, sorry. Yes. And delta of psi plus minus is equal to psi plus minus times psi plus minus. Here I ignore the central elements which appeared in the shift of the parameter z of the variable z, but more or less formulas are like this. So this is a formula like we have if we think that x plus is e, psi plus is k, then these are the standard formulas. And it is an easy computation, which probably should do in the lecture, but not now, that this coproduct is actually well defined. So it preserves all these formulas. And the theorem, okay, so let me state it first. Okay, first, it is easy, it is lemma. Delta nu is coproduct. Actually, it is topological coproduct, whatever it means. So it means that the coproduct of the element will be some infinite sum, which is not well defined in arbitrary representation, but for highest weight representation, it is well defined. But this is a problem which actually we have even for R matrix. R matrix is an infinite sum, and it is well defined in the highest weight representation, but not, for example, evaluation representation, which they are not highest weight. So R matrix should be somehow defined properly. I will put this in the problems because I want to start. But what I wanted to say at the end of the lecture, that this coproduct, this new coproduct, is actually conjugated by the ordinary one. So delta nu is conjugated to delta by product over beta belongs to phi plus infinity r beta. So in this formula, okay, let me write it more carefully. What we had that full R matrix is some Cartan part times product over negative roots minus alpha r minus alpha plus delta times dot times r. Then R matrix corresponding to imaginary roots. Here order could be arbitrary, such all of them commute. And then product with respect to positive roots from like of the form alpha plus some deltas. And so on. And what I said at the very beginning, if we somehow, we can twist coproduct using one factor here. This will be the action of the braid group on the set of coproducts. Using the action of the braid group, we can define new coproduct from the old one. And Drinfeld coproduct is not obtained by this action, but obtained as a limit of such actions. So we somehow exclude all such factors and as a result, you get new Dirichlet coproduct. In particular, it says that formally, at least formally, new coproduct and standard coproduct are conjugated. So if everything is well defined, then for generic values of the parameters, the corresponding tensor product of the representation should be isomorphic. But because in practice, there are some. Okay, are there any questions? Actually, this is all what I wanted to say today. I just explained the plan and the main facts, and some details with computation I will supply in the notes. I stop.